half-life of radium-226 is 1,590 years. So if a sample contains 200 milligrams, how many milligrams will remain after 2,000 years? Let's look at a couple different ways to determine how we can answer this question. So if I'm thinking about an exponential function, I'm thinking about the form f of t equals a times b to the power of t. You can also do this using the form f of t equals a times e to the power of kt. Both methods will work here. So we're told that the half-life of radium-226 is 1,590 years. So what I'm going to do is I'm going to use that information to first figure out a value for b, and then once I know b, then I'm going to answer my question. So a half-life means whatever we started with, we now have half as much of that. So if a here represents our initial value, I can think about that you'll have 1/2 of that amount after a time period of 1,590 years. So I can set up an equation, 1/2 a, half of whatever we started with, is equal to the initial amount times b, our growth factor, to the power of the time frame that it takes to go from a to half of a. I can look at now solving this equation for b. So if I divide both sides by a, the a's cancel on both sides, and we're left with 1/2 equals b to the power of 1,590. Since I'm interested here in solving for b, I'm going to take the radical with an index of 1,590 on both sides of my equation. So the 1,590th radical of, or the root of b to the 1,590. So this gives us that b is equal to the 1,590th root of 1/2, or another way to write that is 1/2 to the power of 1 over 1,590. It turns out this pattern will always happen when you're dealing with a half-life. So anytime you're dealing with a half-life, when you go to solve for b, the base here will always be equal to 1/2, and the exponent is always going to be 1 over the half-life. So every time we're finding b when we're dealing with half-life, the same pattern is going to emerge. So now that we have this value for b, now we're saying, okay, if we start with 200 milligrams, we're saying if a is equal to 200, and if our b is 1/2 to the 1 over 1,590 power, how much will remain after a time frame of 2,000 years? So we can plug all of this information in and evaluate our function. So f of 2,000 is equal to 200 times 1/2 to the power of 1 over 1,590 all to the power of t, but this time we know a value for t, so rather than just leaving it as t, we can write this as 2,000. When you have a power raised to another power, we can multiply those together. So another way to write this would be 200 times 1/2 to the power of 2,000 over 1,590. This is what we want to put into our calculator in order to evaluate. So if we round to 2 decimal places, we would find that f of 2,000, or the amount remaining after 2,000 years, is about 83.63 milligrams. Now you may have noticed if you watched the help videos for this problem that he describes the method in a slightly kind of compact way, but it's doing the same thing that we were doing. So if you're thinking about our function f of t equals a times b to the power of t, what he said for this particular problem is, since we know the half-life is 1,590 years, we can use that to just write our original equation. So because the half-life is 1,590 years, it must be true that f of 1,590 will be equal to 1/2 of a, half of whatever we started with? Well, since we know that our kind of generic setup is a times b to the power of t, as we're thinking about f of t, if it's a times 1/2, we're thinking about what would that exponent have to be so that when we plugged in 1,590 we got just 1/2 a. Well, that means that the exponent must be equal to 1 when t is equal to 1,590. So if we think about an exponent as t over 1,590, then when you plug in f of 1590, you'd have a times 1/2 to the 1590 over 1590. Well, 1590 over 1590 is just 1, so you'd have a times 1/2 to the first power, or just 1/2 a. So anytime we're working with something where we have a known half-life like this, we could use this setup as kind of a starting point, knowing that as we solved for b, as we did on the previous slide, we ended up with b was 1/2 to the power of 1 over 1590 when we took that 1590th root to find our value for b. This is just kind of saying, well, if this pattern happens every time, let's just go straight to this format. So then we could take the given information. We're told that, okay, well, if a is equal to 200 and t is equal to 2,000, plug this into your function. So we'd have f of 2,000 is equal to 200 times 1/2 to the power of 2,000 over 1590, which is the exact same calculation that we were doing before, and so it's still going to be equal to 83.63 milligrams. So both of these are accomplishing the same thing. It's just two different ways for us to be able to go at this. So in the first method that we took a look at here, we actually solved for b by plugging in a and 1/2 a, but we came up with that same base of b and then evaluated. In the second method, which is what you see in some of the help question videos, it's just another way to write that initial equation.